6.3 Integration by Parts, Part 1. Your objective for this lesson is to integrate by using integration by parts. The first thing that you need in order to integrate with integration by parts is this formula. So the integral u dv is equal to uv minus the integral v du. Example 1, we're going to evaluate the integral of x cosine x dx. So first of all, I'd like to point out how this is different than what we were looking at in the last lesson, which was integration by substitution. You can see here that if I try to replace one of these with u, so if I said, for instance, u equals cosine x, when I went to find du, that's going to be negative sine x dx. And I mean, I could get the dx by itself, but that still leaves the x here. And now I've introduced a sign into the picture, and that really just complicates things. If I replaced x with u, then I haven't really changed anything. I've just changed the letter. It hasn't actually done anything helpful for me. So here we're going to use integration by parts. Again, that formula was the integral u dv equals uv minus integral v du. And in this case, I'm going to say that u is x. So u equals x. So du, the derivative of x, is dx. And cosine x dx will be our dv. So dv is cosine x dx, which means that v, so if we integrated cosine x dx, we would get sine x. And now with this information, we can plug into the second part of the formula. So we get x sine x minus the integral sine x, and du is dx. Okay, and we've been left with an integral, but this is a lot easier to integrate. You can see we only have a sine x now. And that's one of your basic trig formulas. So that integral is negative cosine x plus c. So we have x sine x plus cosine x plus c. Okay? Example 2. What are the choices for u and dv when we apply integration by parts to the integral x cosine x dx? So this is the problem that we just looked at, and what you probably are thinking is, well, how did you decide what to use for u and what to use for dv? Well, there are 4 possibilities here. 1, we could have said that u equals 1, because this is 1 times all that, and dv is therefore x cosine x dx. This does absolutely nothing for us. Nothing. So that's kind of useless. Our second possibility is what we did use, which was u is x and dv is cosine x dx. So we used this, and you saw that that worked very well. Third choice, so this was good. Third choice, u is x cosine x and dv is dx. Well, if we did this, then we would have du is, gosh, what is du? Well, using the product rule here. sorry. So the first one, x times the derivative of the second one, which is negative sine x, plus the second one times the derivative of the first, so we get this. And then our v would be x. So we would end up with uv, so x times x cosine x, so x squared cosine x, minus the integral of negative x sine x plus cosine x dx. Okay. And I can keep going here. So that negative I can kick out and I get plus the integral of x sine x plus the integral of cosine x. And really, I mean, no. I still have this here. I haven't really done anything, gone anywhere. I'm going to keep going in circles. Fourth possibility would be that u is just cosine x, and then dv would be x dx. So this would make du negative sine x dx. And v here would be 1/2 x squared. Okay, so then we get our integral is equal to cosine x times 1/2 x squared with x squared in front, minus the integral negative sine x dx times x dx. And you can see here that this is basically the same thing that we had up here. That's also pretty bad. So really, those two are just very messy. We want to stick with number 2. Of course, it is very cumbersome, time-consuming to go through all of the different possibilities every single time you have to integrate using integration by parts. So use this little acronym to help you choose and remember the order. Lipit. So this is how you're choosing u. Your first choice is a natural log. Your second choice is an inverse trig function. Third choice is a polynomial. Fourth choice is an exponential function. And your fifth choice is a trig function. So Lipit. That is how you choose u. Example 3. Find the area of the region bounded by, so it should be bounded by the curve y equals x e to the negative x and the x-axis from 0 to 3. So x equals 0 to x equals negative 3. So really we are integrating, so area means integrate, from 0 to 3. The function x e to the negative x dx. Okay, and I can see here that x is not really a derivative of e to the negative x, and e to the negative x is not a derivative of x. So we're going to have to use integration by parts. Okay, so who's my u? Well, I have a polynomial function, that's x, and I have an exponential. Polynomial comes before exponential and Lipit, so I'm going to say that u equals x. And then dv is e to the negative x dx. From here I'm going to find du, which is just dx. And I'm going to integrate this to find v. So this is going to be negative e to the negative x. Okay. Now my integration by parts formula is uv minus the integral v du. So I have x times negative e to the negative x minus the integral negative e to the negative x dx. And I can boot that negative out. So I have negative x e to the negative x plus integral e to the negative x dx. And when I integrate e to the negative x, I'm going to get negative e to the negative x plus c. Okay, so this is what my indefinite integral was. But I had a definite integral, so I need to evaluate this. So this integral 0 to 3 x e to the negative x dx equals negative x e to the negative x minus e to the negative x, evaluated from 0 to 3. So we have negative 3 e to the negative 3 minus e to the negative 3 minus 0 e to the negative 0 minus e to the negative 0. Okay, so I'm going to treat these e's like x's. If I had negative 3x minus 1x, I'm writing e still, I would have negative 4x. So here I have negative 4 e to the negative 3. Over here, e to the negative 0 is e to the 0, which is 1. Of course, 0 times anything is 0. So I have 0 minus 1, which is negative 1. Minus negative 1 is a plus 1. So this would be my exact answer right here. If I wanted to approximate that to 3 decimal places, let's see what we would get. So negative 4 e to the negative 3 plus 1. So I get 0.801. I'll say. So 0.801 is approximately my area. Example 4. Evaluate the integral x squared e to the x dx. So again, remember Lipit. I don't have a natural logarithm. I don't have an inverse trig. I do have a polynomial, and that is x squared. So I'm going to say u is x squared. dv is e to the x dx. du is 2x dx. And v is e to the x. Okay. So now I know I have uv minus integral v du. And that is x squared e to the x minus the integral e to the x times 2x dx. I'm going to kick my 2 out. Goodbye. Okay, and this, wow. So I think I'm going to have to integrate again using integration by parts, because you can see I still have this tricky integral here. So I'm going to actually integrate again. You can do that. You can integrate using integration by parts more than once. So here, u is an x, so du is dx. dv is e to the x dx, so v is e to the x. Okay, so let me move this whole part over. So this front part stays the same. It's just my integral that's changing. So I'm going to have uv, so x e to the x, minus the integral of v, so e to the x, times du, which is just dx. And now you can see that this integral will finally go away. Finally. And we just end up with e to the x plus c. Okay, and our last order of business here is to distribute that 2. So e to the x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Remember that even if I multiply 2 by c, it's going to stay a c. No matter what you do to that c, it's still a constant. Even if the constant is different, it's still a constant. C just stands for constant. And this is our answer. And that is the end of part 1.